Okay, hello everyone. Good afternoon. Dr. Nat here. So we are still in week 2, but I already feel tired. So this is class ECC 3129, week 2, part 2. So sorry, I had to cancel class on Wednesday because I'm part of Innovathon. I'm not sure if you know about that TV show. It's a TV show where I have to pitch about my research product. So it's a competition, and there are 56 contestants picked from all over Malaysia. So they come to UPM, not really UPM, they come to Astro to pitch their product. And penat lah. It's very tiring. So yesterday was the rehearsal and it ended, so it started from 11 a.m. and it ended at 10:30 p.m. So very, very tiring. And on Wednesday, we had coaching with Pak Aznil. So I don't know if you know Pak Aznil. He's like 50 years old already. So, but during my time when I was younger, so Pak Aznil ni was like booming lah. So now he's like a mentor to the celebrities. I'm not a celebrity, I'm just pitching my product. Okay, so nanti when you see the Innovathon show, please sokong saya. Please vote for me. Not that you can vote anyway. But yes, please support me. Alright, so we are going to continue on amplitude modulation. So as usual, I am recording this class. You can go back to it. I have already shared the slides. What else? So if you have any questions at any point of the lecture, please feel free to interrupt as usual, okay? So recap a bit on AM modulators. So we talked about AM modulators last Tuesday, and we know that we need to have a modulating signal where we call it as V. V means instantaneous, small vm means instantaneous modulating signal. The unit is going to be in voltage, and then we also need to have a carrier signal. And the condition for a good AM signal, when we combine these two together, is that the instantaneous carrier signal needs to have a greater frequency and a greater amplitude than the modulating signal. So that was the condition. And when we feed it into an AM modulator, what we're going to get is called an AM signal. Okay, so we're going to write this as VAM. And in this case, they label it as V2 because it was part of the derivation that we did. But most of the time, we will use this term VAM. It means AM signal that has been combined with modulating signal with the carrier signal. So this was the equation that we talked about. So VM is, this is a fixed value. Okay, VM needs to be less than VC. That was the condition. And then this is a sine of 2 pi frequency of the modulating signal times with time. And then we have the VC. Okay, the VC is the peak voltage of the carrier signal times with sine of 2 pi FC. FC is the carrier frequency and times with time. Okay. Combining these two into an AM modulator will give you an AM signal, which is the following. So we have this guy. So that's VC. And then this is VM. And this is like almost VC, but not really. So it's just the sine of this VC. So you multiply. Okay, so what you're going to get is an envelope, AM envelope. Okay, so whereby this shape is your VM shape. Okay, and then it is reflected, or like it's symmetrical, almost reflected like mirror. This is the original shape. It's going to be doubled, reflected below, and inside is going to be your carrier signal. So this is how it looks like. And in week 4, you're going to see, no, I think it's going to be in week 5. Week 5, you're going to see how AM signal looks like, exactly like this. Okay, and you will do it yourself using the circuit. It's pretty cool. Okay, moving on. We also talked about tone modulation which also means modulation. So just ignore the word tone. It just means modulation. So 50% modulation means that you're going halfway off the peak. So you have your peak VC, you're going halfway down. If it's 100%, you're going all the way down, which means that you are not leaving anything there. So it's completely at zero. This was at 0.5. This one goes all the way down to zero. And then if you over modulate, which is bad, skull icon, you are overlapping, you are going below zero, which means that this guy is going to overlap, and this is not good. Okay, so just recap, this is what we have already discussed last Tuesday. Okay, and then we also talked about modulation index. My voice. We also talked about modulation index. Okay, modulation index is given by M. Now don't get confused with modulating signal, because a modulating signal is Vm. Okay, this is just M. Okay, so M is Vm over Vc, and Vm is Vmax minus Vmin, and Vc is Vmax plus Vmin. Okay, and we did not do an example yet, I think. Okay, let's do an example. Okay, suppose that on an AM signal, okay, so we have an AM signal, the value Vmax peak to peak read from the graticule of the oscilloscope, just ignore this, read from the oscilloscope, okay, screen is 5.9 divisions and 1.2 divisions. So how does this look like? Oh, let me try to visualize this, because you have not started lab with me yet. Oh, I don't want this. Skip that. Okay, let's try to make the oscilloscope screen, because why not? It's Friday. Let's take it easy a bit. Ada ke yang kosong? Oh, okay, this one. Okay, so imagine this is your oscilloscope. Tak cukup pula. Okay, give me a minute. Insert rows above. 5.9 division, 1.2 division. Okay. Let's make this smaller. Okay. Now I'm going to draw again. Whoops. Okay, so it says that on the oscilloscope screen is 5.9 division is the Vmax peak to peak. Mana tulis? Oh, Vmax peak to peak, 5.9. Okay, let's write that down somewhere. Vmax peak to peak is 5.9. And then we have Vmin peak to peak, 1.2 divisions. Okay, when they say division, it just means the boxes. Okay, so let's say we start from 0. I cannot start 0. Let's start 0 here. So this is 1 box, 2 box, 3 box. Okay, let's label this 1, 2, 3, 4. Lama tak cukup. Okay, ulang balik. Okay, 0, 1, 2, 3, 4, 5, and 6. Okay, so it's saying that the maximum peak is, oh, I still don't have enough. Oh, okay. It's 5.9. Okay. Okay, let's go back to the term peak to peak. What does it mean? Vmax peak to peak is from the top to the bottom, all the way. It's not, we're not starting from 0 here. If we're starting from 0, it's just called Vmax. If we are going from top to all the way to the bottom, it's called Vmax peak to peak. Okay, so when it says that the Vmax peak to peak is 5.9, which means that from here to here, it's 5.9 boxes. So I need to use 6 boxes to draw this. Okay, I'm going to try my best. So this is not the way to draw it. Okay, 0. So 3 above, 3 down. Okay, let's just try. Okay. Okay. Okay, okay lah, good. And then I'm gonna make this symmetrical, supposedly. It's so ugly. Okay. Okay, so from here to here is 5.9 divisions. And then the V min, which I did wrong, is 1.2. So I need to have like from here to here maybe. So I need to redraw this. So it will be, let's use a different color. Susah tau nak lukis wave. Macam tu ke? Bad. Korang layan je lah saya Okay. Okay lah. Okay Cakap je okay. Okay. Alright, so this is this is how it looks like. Okay, thank you, Shafiq. Alright, so that is your Vmax peak to peak, and this guy is 1.2. Okay, so with this information, we can actually calculate the Vmax, the M, which is M is equal to Vm over Vc, whereby it is also, this is too thick, V max peak to peak minus V min peak to peak divided by V max peak to peak plus V min peak to peak. Okay, the values are given. It's not in voltage, but we can still work with it because this is a ratio. When you have values that can be cancelled out, you can get the ratio, right? So V max peak to peak of 5.9 minus 1.2 is, I wrote it down somewhere, is 4.7. So 5.9 minus 1.2 divided by 5.9 plus 1.2. So this is going to give you 4.7 over 7.1, and this is M. So M, there's no units for M because why? The units above is cancelled out by the units below. Okay. So what is the modulation index? So M is, somehow I did not punch the calculator for this. So let's just use it in ratio. Okay.
0.66.
0.66. Yay, thank you. So if they ask you what is the modulation percentage, so you just multiply this by 100%. So you will get 66%. So you have two answers. This is just M, modulation index, and this is modulation percentage, which is just the percentage. So that's the first question. Now it's asking us calculate VC, Vm, and M if the vertical scale is 2 volts per division. So now it's telling us one box of this is actually 2 volts. Okay, so if I were to label this is going to be 2, 4, 6, 8, minus 2, minus 4, minus 6, minus 8. Okay, so do I have to calculate 5.9 times 2 volt and then do this calculation all over again? No, I don't really have to because I already have this and this. Okay, now I need some space. Let me duplicate this. Okay, and then let's get rid of this drawing. Do I need it? No, I don't need it. Okay. My hard work has been erased. Okay, wait. Okay, get rid of this table. And then let's put this somewhere visible. Okay, let's put it there. Okay. So this was the first question, A. Okay, so B, calculate VC and VM. Now remember, M is basically VM over VC. And you already know it's 4.7 over 7.1, which means that VM is 4.7 divisions, VC is 7.1 division. So we can just find out what the value is. So 4.7 division, whoopsie, division times with 2 volt per division. So what you're going to get is 9.4 volts. And then for VC, it's 7.1 division times with 2 volt per division. You're going to get 14.2 volts. This is a 4. Whoopsie. Yeah, that looks like a 4. Okay, let me just write it again. Okay, so that is 14.2. So that is your voltage for VC and voltage for VM. So what is the modulation index? It's still the
Betul,
same.
betul.
Yes.
Tak payah divide by 2 ke?
Yeah, divide by 2. Oh, you
Yang
are correct. Betul, betul. You are correct. I forgot about this. So if you are correct, Shafiq, I forgot about this division. Okay, so divide by 2. Let's go over this one. See, yes. Okay. So basically it's divide by 2. Okay, so this is VMBC. So VM is Vmax minus Vmin, right? Divided by 2. Okay. We can, let's not skip steps. Okay, let's just use this. So you get 4.7 divided by 2 times with 2, so it's 4.7 volts. Okay. Let me rewrite this so that everyone does not get confused. Okay. Equation Vm, Vmax minus Vmin divided by 2. Vc is Vmax plus Vmin divided by 2. So we already have 4.7 division for this answer divided by 2. And then this is going to be 7.1 divided by 2. This is in division. So we want to get rid of division. So now I'm going to multiply this by 2. Okay, times with 2 volt per division. And then this is 7.1 over 2 division times with 2 volt per division. So that cancels out. This is 4.7 volt, 7.1 volts. Kejap. Let me find some space. Okay. Sorry, I don't have space. Okay, so I'm using this. Was that okay? Faham tak? Was that confusing? Because I totally forgot about the divide by 2. Thank you, Shafiq.
okey je.
What about the rest? Thumbs up, thumbs down? Okay, alright, thank you.
Sebab mula-mula saya try ambil direct juga. Lepas tu macam tak dapat. So saya guna formula.
Okay, good. Okay, moving on. Sidebands and frequency domain. So what we have talked about so far is these kind of waves, right? And these kind of waves, when it is already in AM, when it is in VAM, you can't really tell which is the carrier. Where is the carrier? Where is the VM? How do I, we know the shape is supposed to be VM, right? And then we know that the carrier is somewhere inside here, but ultimately you can't like take it out because it's already like combined together to become one frequency, one wave. So this is this is where we convert the time domain into the frequency domain. Okay, so bear with me on this. So we have A, our modulating signal, And then C is our carrier. Okay, this is our M. Let me write this as VM, VC. Now we have another wave that is slightly smaller, and this is called the USB, upper sideband, and this is called lower sideband. So where did it come from? So we're going to find out. So these guys combined together will form the VAM, the VAM. Previously, when we talked about the VAM, we were saying that, oh, okay, it follows the shape of VM, and then this guy is the carrier. But how do we actually get the carrier to be like this, right? So it must be like a combination of some other stuff. So this is the other stuff that we need to talk about. So the time has come to talk about how to get this wave in its actual form. So when signals of more than one frequency make up a waveform, it is better to show the AM signal in the frequency domain. When presenting in time domain, the presence of sidebands is not obvious. This guy has sidebands, but you can't really tell because, it's a single wave. Okay, so how do we calculate the sideband? We want to find out what is the frequency for the small waves that is part of the AM wave. Okay, when only a single frequency sine wave modulating signal is used, okay, or we can say FM, the modulation process generates two sidebands. The modulation process produces two sidebands. Okay, if the modulating signal is a complex wave. Now, what we talked about here is a non-complex wave because it only has one frequency. So having one frequency is the best because it's easy. But when it is a complex wave, it means that we have a bunch of frequencies making up the modulating signal. So instead of like this is a very nice wave, it's a very basic. We have something that, okay, that is not supposed to look like that. Let me try again. Something like that. So you have like a bunch of frequency. This is a different frequency, this is a different frequency, and the combination of that produces something like this. This is a complex modulating signal. We love this kind of signal. This is a little bit hard, but we can still work with it. Okay, so how do we calculate the sideband? So sideband is basically FC plus FM. FC being the frequency of the carrier, FM is the frequency of the modulating signal. So if the FM is a single frequency, so you are in luck lah. You can just use this equation easily. So now, how did we get this FC plus FM, FC minus FM? So it lies in this equation, this part specifically. So it is a multiplication of two signs. And we have learned in your math class that when you multiply two signs together, you get something like this. This is trig identity. So you thought you're not going to see it? Yeah, well, it's back. So sine A times sine B, you get this expansion. So, so okay, so sine here, now it's cosine. So your FC is your A, your FM is your B. So cosine of FC minus FM, right, over 2. And then you have cosine FC plus FM, okay, like that. So, okay, obviously I need to have the 2 pi t thing, but kita buat simplified. Minus in here, and then this is going to be divided by 2. Okay, so if I were to rewrite this properly, so not to confuse you, let me write this again. So this is going to be cosine 2 pi. So the FC is going to be minus with FM, right, like that, T. Okay, this is A minus B. Okay, that's where it comes from, divided by 2. This is this guy. Okay, now the second guy, minus cosine, don't have space, minus cosine 2 pi. Fc plus Fm T divided by 2. Okay, so this is the second part, which is A plus B. Okay, so basically what we did was we have these two signs multiplied together. We converted into, we used the trig identity, expanded it, and we found out that, oh, okay, we have an lower sideband, okay, and an upper sideband. Okay, so how does this look like in the frequency domain? Okay, so this is the completed equation. Okay, and this Vm over 2 minus Vm over 2 is basically this guy. Okay, this is multiplication, right? So when that happens, how do I write this? Okay, let me duplicate this. Okay, I have duplicated this, so let me get rid of some stuff. So at any point you are confused, please ask. I want everyone to understand this as best as you can. Oh, sorry, that was the rooster that my neighbor has. Oh, wow, it's going to be in my recording. Okay, that's okay. Okay. Okay, macam ni. Okay, let me redo this. Not redo lah, cantikkan je. Okay, so we already talked about this guy. Where did the VM come from? Okay, so your VM, the expansion, okay, it's here. So your VM is here. Okay, your VM is here because basically it's VM multiplied by sine, right? Okay, so it's basically like this, which means that it's also like this over here, VM. Okay, I have this 2, which is the common denominator for both of these guys. So I can take it out to become Vm over 2. So I get cosine A minus B plus minus cosine A plus B. Okay, something like that. So I do whatever math that I need to do. I get something like this. Now I bring it back and multiply with these terms back. So I'm going to get Vm over 2 here and Vm over 2 here. Okay? So it did not come out of thin air. It's been there all along, but we took it out first, solve for the trig, put it back together. So if you can just multiply everything and not get confused, by all means just do Vm over 2 and then find out this guy with this guy. If you want to do the trig first and then take out the Vm and then put it back again, do whatever works for you as long as the math is correct. Okay? All right, so how do we draw this in the frequency domain? That was the math. The math told us that we have lower sideband and upper sideband. Frequency carrier, and the FM is already becoming this. So these are the frequencies in our equation, 1, 2, and 3. This is the VM. There are 3 frequencies. When we have expanded everything, we have FC, we have FC minus FM, we have FC plus FM. So let's try to draw this in the frequency domain. So this is the frequency, this is the carrier frequency. This is the upper sideband frequency, which is FC plus FM. And this is the lower sideband frequency, which is FC minus FM. Okay, so 3 components that I saw in my math equation. This is what is represented in the frequency domain. And then let's talk about the voltage. The voltage for this is just Vc, and the voltage for the upper sideband and the lower sideband is exactly the same as our math equation. So let's bring it back. Let's bring back the equation and see. Okay. Draw. Okay, so we have VC voltage as my peak voltage for the frequency, and then this is FC. Okay, so this voltage peak belongs to frequency FC. So this is what I'm drawing, VC, FC. FC is the frequency. VC is the voltage peak for the frequency. Okay. Excuse me. All right. And then we have Vm over 2. Okay, Vm over 2. And then this is the frequency. Okay, Fc minus Fm is going to get you something in the negative side or something in the left side. And then we have Vm. Okay, let's ignore the minus first. Vm over 2, and then this is the frequency. So this is Fc plus Fm. It's going to be on the right side of the carrier frequency. Okay. So again, Vc must be greater than Vm. So Vm is supposed to be smaller than Vc. So Vm over 2 is going to be it's going to be smaller than Vm, and of course than Vc. Okay, I hope I didn't confuse anyone. Okay, so what is the bandwidth for this AM signal? Okay, bandwidth for AM signal is back to the lecture in week 1, I think. I don't remember. So bandwidth was F2 minus F1. F2 minus F1, very generic. But what it means is the maximum minus the minimum. So in this case, this is going to be your maximum frequency. This is going to be your minimum frequency. So you will use Fc plus Fm minus with Fc minus Fm. So your bandwidth is 2 Fm. Okay, so where did this come from, doctor? Okay, let me do it for you. Because no one wants to ask me questions, I'm asking myself questions. Okay. Let's get rid of this. Right. So let's talk about the bandwidth. Okay, bandwidth is F2 minus F1. Okay, and then F2 is maximum. Always, this is always the case. But somehow they like to use F2 minus F1. I don't know why. So, but in our understanding should be F max minus F min. Okay, so F max in this case is our upper sideband, which is Fc plus Fm minus Fc minus Fm. Okay, so the simple math, you have your Fc minus Fc, Fm plus Fm equals 2 Fm. So the bandwidth for an AM signal is 2 Fm. Doesn't matter what your Fm is, just plug it in. If your Fm is 100, so it's going to be 200 Hertz. Okay? Right, any questions? What time is it? Okay, we have time. Okay, everyone okay? Not okay? Okay, not okay?
Okay.
Okay, all right.
Okay.
Okay, thank you. Okay, so let's talk about the relationship. We talked about the math equation, which was dealing with time, and then suddenly we had to draw it in frequency domain. So let's talk about the relationship, or at least how to visualize between these two. Okay, so we talked about the modulating signal, Vm, right? And then we talked about the carrier signal, Vc. And then we found out in our math, in our equation Vam, that we had three frequencies, Fc, Fc plus Fm, Fc minus Fm. So this is a wave on its own. This is also a wave on its own. This is also a wave on its own. And the combination of this is your AM signal. right? So this is what it's trying to portray here, FC minus FM, FC plus FM, and then this is the frequency. So this frequency is going to be, um, your USB is going to be greater than FLSB. So what does that mean? It means that it's faster. Frequency is faster, right? You can see here, it is faster. This is like a bit slower, not that slow, but slower. Okay, so you have in the frequency domain, this is plotted here. So your carrier is here. Okay, this is the peak, this is the peak, this is the peak, this is the peak. Smaller peak, lower frequency. It's drawn here. Okay, so this is your VAM representation in the frequency domain. You don't have this anymore. Sorry, this is not it. You don't have this guy anymore because it has been combined with the carrier to become this. In the time domain, you will see this guy, time domain. Very hard to understand. In the frequency, it's easier. It's just a bunch of sticks. Just easier for us as engineers. Okay, moving on. If anyone has any questions, feel free to ask, okay? So we have an example here. Whenever the modulating signal is more complex than a single sine wave tone, which means that it has more than one frequency, multiple upper and lower sidebands are produced by the AM process. Okay, what does that mean? So remember we had our beautiful basic signal, which is basically one stick, one frequency. This is a good signal. I mean, it's easy for us, so it's a good signal. So if it has more than one frequency, which means it's going to be complex, it's going to look like, a bunch of squiggles. And it's not going to be a single frequency, but it's going to be a bunch of frequencies that make up this signal. So this is FM, your signal frequency, your modulating wave. Same thing. Okay. So this is our good case, and this is not too good case, but we still have to work with it because we are intelligent engineers. Okay, so here we have an example. A voice signal consists of many sine wave components. So a lot of frequencies, of different frequencies mixed together. Recall that voice frequencies occur in 300 to 3000 hertz range. If you can't recall, I'm telling you, the voice has frequency from 300 to 3000. So we can go like that, right? So those are different frequencies. So if the carrier frequency is 2.8 megahertz, given here is 2800 kilohertz, then the maximum and minimum sideband frequencies are, okay, let's decipher this question. Okay, FM is given as our voice, okay, my voice or your voice from here. So this is our not so great scenario, but we have to work with it. FC is given as 2800 kilohertz. Now, do you want to work with megahertz or kilohertz? Doesn't really matter. So it's giving me kilohertz. I'm just going to use it. If you don't want to use kilohertz, you want to use it in hertz, by all means, use it. Okay, it's the same thing. So now, the question is asking what is the maximum and minimum sideband frequencies. At this point, we know what sideband is. We have two types: sideband, upper sideband, lower sideband. What is the equation? FC plus FM for upper. Upper means higher, right? So obviously it's going to be plus, and then lower is going to be minus. Okay. Now our FM is a range. So it's going to be not a single value. So if I were to visualize this, it's going to start from here, 300, up until 3000 hertz. Okay. What does that mean? It means that everything inside here is the FM. There's a lot, a lot, a lot. So we don't actually draw this. We don't actually draw all the lines because it's basically everything. So you just draw a block and just, what do you call this? Lorette kan shade it. Yeah, shade it. Just shade it. Okay. So this is everything. Within this range is your voice. Your voice and my voice are different, but we have different frequencies. But this is catering all everyone's voice. Okay. Now, how do we find out what is the upper sideband and lower sideband? So we will take the boundary, the boundary. So this is lower boundary and this is the upper boundary. Okay. So FUSB, so I'm trying to work with the lower boundary first. So FC plus FM lower boundary. Okay. And then FC plus FM upper boundary. So this is going to give me 200.3 kilohertz, and then this is going to give me silap terbalik, betul-betul lower. Okay, FC and this is upper. Okay, this is going to be 3000 in kilohertz is 3, so 2803 kilohertz. So my upper sideband has a range of 2800.3 all the way to 2803 kilohertz. Okay, so that was one side, that is upper sideband. Now let's find out the lower sideband. Let's duplicate this. Should get, okay, let me get rid of this. Okay, now working on with F lower sideband. Okay, the equation is FC minus FM lower. Then we have FC FM upper. Yes, because it's the range, right? So we have to find out. So FC is 2800 kilohertz minus with 0.3 kilohertz. This is going to be 2799.7. Okay, I did that. And then this is going to be 2797. Okay, hopefully this is right. Kilohertz. Okay, so how do we draw this? Okay, drawing. FC. Okay, 2800. Let me write the values. Why do I always not have space? Let's get rid of this. Put this up here. Okay, and then let's move this over here. Okay, again, any questions, feel free to ask me. Kairis ni macam keluar masuk Is your internet okay? Okay, so this is how you draw it. Wow. Okay, FC is going to be here, 2800, and my axis is kilohertz. Okay, because everything is in kilohertz at this point. So we know that our upper sideband starts from here all the way to 803. So this is your FUSB. Okay, this is FC. And then same case over here. You have your FLSB. And this is between 2799.7 to 797. Okay, that is how you calculate if your FM is a range. Any questions about this? Is this confusing or if this is okay? Do you understand it?
Doktor, can I ask?
Yes.
Kenapa 2800.3?
2800.3 because 300 is in hertz. I am working with kilohertz, so if I convert this to
Ah,
kilohertz,
okay.
0.3. Okay. Any other questions?
Doktor, final answer dia yang graph tu ke?
Okay, that's not the final answer. Then the maximum and minimum sideband frequencies are sideband frequencies, maximum and minimum. This is you have to give the range. So upper sideband is going to be 28.3 to 2803. Okay, range bukan tolak. And then lower sideband is going to be 2797 to range 2797.7. If they ask you to draw, then draw. If let's say you give me this answer and you give me the answer, I accept it because it shows me that you understand. Kalau tak buat range macam ni pun, if you give me this, it's acceptable. So basically drawing is your best way to get maximum marks lah, because it shows me that you understand. Okay. Okay, so this is the answer that I got from the textbook. So you can use this. So this is the bandwidth. If they ask you the bandwidth, then yes. The 2803 minus 2797. I feel like the question is asking you SP and LSP rather than bandwidth. So if they ask bandwidth, I would add find the bandwidth. Okay, let me just write that over here for this AM signal. Okay. So we have 9 more minutes. Let's do one more and then let's end class. Okay, one more. Bear with me. A standard AM broadcast station is allowed to transmit modulating frequencies, oh no, my battery, up to 5 kilohertz. Okay, let's just do it. If the AM station is transmitting on a frequency, whoops, standard AM broadcast station, okay, remember, if you don't know this, your radio has FM and AM station. Tahu tak? Tak tahu Ke tahu? I don't know if you know.
Tahu.
Tahu? Okay.
Tapi tak pernah terfikir pun itu apa dia.
AM radio and FM radio. Basically, you don't actually use AM radio, you only use FM radio, right? Then there's a bunch of channels. You have hits, you have era, you have apa lagi? Tahulah. Something. So these are different frequencies. So AM radio, we don't really use it, but it is used by, I think, military sometimes use it. But basically they don't use public frequencies. The frequency that they have is a secret. So we can't really tap. Okay, so a standard AM broadcast station is allowed to transmit modulating frequencies up to 5 kilohertz. So it says up to, which means that it can be from 0 up until 5 kilohertz. This is your FM. Okay, if AM station is transmitting on a frequency of 980 kilohertz, when it says transmitting on, it means that is the carrier. So this is your FC carrier frequency. So it is 980 kilohertz. Okay. Compute the maximum and minimum upper and lower sidebands and the total bandwidth occupied. So it's asking USB, LSB, and B, occupied by the AM station. So let's find out. This is pretty easy because it explicitly says that what they want. Okay, FUSB is just going to be, remember your FM is a range, so your first boundary is 0, so you can't really add 0. I mean, you can't really do anything about the 0, so let's just calculate with 5. So it's going to be 980 kilohertz plus 5 kilohertz. So that is going to be 985 kilohertz. And then your FLSB is 980 kilohertz minus 5 kilohertz. You will get 975 kilohertz. Now, if I were to draw this, oh wow, okay. If I were to draw this, okay, this is your FC, which is 980. Let's assume this is in kilohertz, so it's going to make our lives easier. So it says that it goes from 0 to 5. So this is your upper sideband, right? 985. This is your lower sideband, 975. It goes from 0 to 5 kilohertz, which means that everything within this range is your upper sideband. And everything within this range is your lower sideband. And basically, this is how a radio looks like. The bandwidth for a radio, it has a carrier. Let's say Hz is 98.5. So the channel is from here to here. So if you tune it between here to here, you can still get Hz channel because that is where everything, it occupies the whole bandwidth. Okay, but of course, if you put your frequency radio to the carrier, it's going to give you the best signal. Okay. Okay, so now what is the bandwidth? The bandwidth is basically F max minus F min. So that is going to be 985 minus 975, which is 10 kilohertz, which is also 2 FM that we discovered earlier. Okay, sorry about the bad handwriting. This is rushing. Okay, so that is all for today's class. What we learned today is we talked about examples for we talked about the math equation and how we use trig to expand it, and we found out, oh, we have an upper sideband and lower sideband. No wonder it looks so complicated. Yeah, so and then we tried to plot it in the frequency domain. So we have 3 frequencies for the AM signal. It's FC, FUSB, FLSB. Upper sideband, lower sideband, carrier frequency. And then we also tried to relate the time domain with the frequency domain. And then the peak of your frequency domain is basically the peak of your sine wave. Perasan lah, okay? Sama, the value is the same. Then we did a bunch of examples and we found out that FM can be a range. It's not just a single frequency. And what happens if it's a range? So it's going to occupy the entire bandwidth. Okay, so that is it for today's class. Thank you everyone for attending. Hope you understand everything. Please revise if you don't. Ask me questions if you have any questions later on. Okay, thank you everyone. My battery is dying. Take care everyone. Have a good weekend.
Thank you,
Yeah,
Doctor.
okay.
Bye.
Thank you, Doctor.
Welcome. Bye. Finish recording. Stop recording.